Hello everyone, my name is Int'l. Today I will present our paper, Example-Based Vulnerability Detection and Repair in Java Code. The Java platform provides various APIs to facilitate security-related features implementation. Recently, studies shown that many developers misuse these APIs and introduce vulnerabilities to their software. For example, JCI provides a class cipher for encryption and decryption. To create a cipher object, developer can call the API cipher.getInstance with a string value. However, if the string is DES, the adopted block cipher is proven to be broken, and the encryption algorithm turned out to be insecure. Instead, developers should call the API with some other options, such as AES, GCM, no padding. Many tools were proposed to identify the security API misuse. However, most of them identify security API misuse with the predefined rules. Users cannot easily extend this tool to detect more API-related vulnerabilities. Moreover, they reported API misuses without suggesting any customized fix. Developers' lack of cybersecurity knowledge have difficulties to fix those issues independently. To address the limitations mentioned above, we propose Int'l, an example-based vulnerability detection and repair tool in Java code. Int'l includes two threads, pattern inferences and pattern application. Pattern inferences target at extensibility of the detection rule set. Developers just need to provide the insecurity and security code pair. Int'l can automatically infer the detection and fix pattern from the code pair. Even with more security library immersion involved, Int'l can still have good extensibility to keep their pattern set of API misuse up to date. Pattern application will not only provide vulnerability detection, Int'l also provided the customized repair suggestions to developers. Through the fixed suggestions, Int'l can help developers better understand the reported misuse and guide them to fix those issues. To facilitate our explanation of the approach, here we provide a running example. Suppose that a security expert wants Int'l to detect the vulnerabilities. The secret key spec constructor should not get involved with a constant as its first parameter. To demonstrate the vulnerability and related fix, the expert can craft the following insecurity and security code pair and provide them to Int'l. Given the insecurity and security code pair, Int'l compares codes to locate the program differences. Once it identifies an updated statement, Int'l locates the security API directly or indirectly used by the updated statement. In this example, the critical security API is secret key spec constructor. By further extracting the program differences with the updated statement, Int'l recognized and recorded the parameter usage differences. After locating the critical security API, Int'l further locates related edits of that statement through the data dependency analysis. Namely, if the updated statement data depended on the surrounding code, or the other statement data depend on the updated statement. Int'l can group all these statements and include them into the pattern as added relevant context. In this way, Int'l ensures the derived pattern is applicable to programs which contain different program contexts. Finally, Int'l abstracts all concrete identifiers using the inferred pattern, so that inferred pattern is also applicable to programs have different identifiers. The resulting pattern includes two parts: the vulnerability templates containing matching related data and the abstracted fix. At the end of this phase, depending on how many code pairs are provided to Int'l, the tool can generate a variety of patterns for later usage. In phase 2, developer can rely on Int'l to detect and fix vulnerabilities in Java code based on its pattern set. Specifically, given a program, Int'l first tries to search for pattern match in the codebase by looking for any usages of critical security APIs. If the API invocation is founded, Int'l can conduct the inter-procedural backward slicing as needed to check whether the API is invoked with an insecurity parameter options. Otherwise, if an API is overridden, Int'l conducts a basic string match to see whether the API is overridden insecurely. For example, as the backward slicing shown here, the API is called with the in-security parameter options constant array. A vulnerability is detected and reported. By customizing the abstract fix for particular program context, Cedar suggests a program-specific fix to developers. In particular, instead of using constant value for first parameter, the fix uses a key derived from an unpredictable random values and create the key by defining an actual function. We crop the 28 code pair and Cedar generates 21 unique patterns, which covers API misuse related to certain APIs. We use the pattern set to further evaluate the detection and fix. To evaluate the detection capability, we leverage a third-party dataset which includes 10 Apache projects with 86 vulnerability labeled as ground truth. We selected 100 popular Apache projects which involve the APIs in our generated pattern set. We use this dataset to evaluate the effectiveness of the fix suggestions. We compare Cedar with the set of R2s, CogniCrypt, CryptoGuard, and FineSecBugs. We found that Cedar outperformed existing tools by achieving highest precision recall and F1 score on average. We manually checked 77 fixes generated by Cedar based on 100 Apache projects and found 76 of them to be correct. It indicates that Cedar can have a great capability of repair suggestions. This concludes my talk. Thank you for attention. Do you have any questions?